Before we go beyond, we need to do a bit of complex analysis and introduce the residue theorem. I am only going to tell you how to use it. I'm not going to prove it. For that you will need to look at a complex analysis course. So in complex analysis we deal with complex numbers and functions of these complex numbers. Consider the case where f is a ratio of two functions, p and q, where p and q are polynomials of z. Obviously, when q is equal to 0, we have a division by 0, which is ill-defined, and we call the corresponding point in the complex plane a pole. An important difference between an integration over a real or a complex variable is that in the case of a complex variable, the integration depends on the path in the complex plane. So this integral will be different if I change gamma by another path. We often consider closed contours. If the contour does not contain any pole, the integral will be 0. However, if it contains one or several poles, it will be a C-number. In fact, an integral on a closed contour is only determined by its poles. Therefore, if I take another contour which has exactly the same poles, the value of the integral will be the same. But it will be different to integrals over contours which contain other poles. We now define a residue for the function f associated to a pole. By definition, it is a ratio of the function p evaluated at the pole divided by the derivative of the function q evaluated at the pole as well. The residue theorem tells us that the integral of the function f on a closed contour is proportional to the sum of the residues of f for the poles which are inside the contour.